Hello and welcome everyone to this Dynaflow webinar. My name is Thijs Krijger and I'm a project engineer here at Dynaflow Research Group. The topic of today's webinar are the effects of modeled support stiffnesses on the mechanical natural frequency of piping systems, which is of particular concern to reciprocating compressor systems and pulsation studies. But the knowledge of this webinar can also be applied to other systems that are dynamically loaded. Let me first start out by introducing our company, for those who are first-time listeners. Dynaflow Research Group is an engineering consultancy firm where we believe in the fun of solving the most challenging of engineering projects. To do this, we employ highly skilled engineers with strong academic backgrounds. All of our engineers hold a technical master's degree in aerospace, applied physics, mechanical engineering, etc. And 20% of our staff holds a PhD. After solving the complex multidisciplinary problems, our engineers will try to propose practical solutions. And some of our work involves root cause analyses, which are performed in the field, at site, at the client. We also do vibration measurements if our client experiences issues with vibrations. Because we believe quality is important, we are an ISO 9001 certified company and have been so for many years. We have a dedicated staff for internal software development, and we focus on the sharing of knowledge through webinars like this one and training courses that are offered as well. We are an independent consultant and we work with owners, operators, EPC contractors and suppliers. And our work focuses on the dynamics and flow through piping and pressure vessels. In this webinar, we'll first discuss the basics of modeling support stiffness. Then we'll discuss dynamic effects which come into play with different modeling techniques. And we'll finish up with a demonstration of how to model support in BOSpulse and the different ways you can use to approach this. So what we'll be talking about today are piping softwares that use a beam type element to perform the calculations. And elements are connections between nodes with the properties of the element determined the stiffness, the mass, etc. At nodes, the user is allowed to define restraints or supports, and these limit the movement of the node. They can be applied in different directions. For example, a restraint can be only limiting the movement in the vertical direction, in which case we'll talk about a rest or a rest with a hold down. It can be a guide when the node can also not move in the lateral direction. And it can also be anchors, which, depending on the implementation, limit the movement in all three directions, as well as limit the rotations. In most piping software, which are used for solving static problems, these supports are modeled as either infinitely stiff or with a stiffness so high compared to regular piping materials that the stiffness might as well be infinite. And this is what we call method 1 for modeling support. And we'll refer to this as infinite support stiffness. Computationally, this is a simple boundary condition and it's fast to model and to solve. And the method overestimates the static reaction loads on supports, specifically if two restraints are working against each other. And this is conservative when only static loads are applied to a system. And so this will lead to a support design that's acceptable for static loading conditions. But in the real world, a pipe support is not infinitely stiff. Take for example this pipe guide support on top of some steel beam. When we apply a force to the pipe, the support beam will bend somewhat. And how much it will bend will depend on how thick and how long the beam is. Here we give a formula for calculating the stiffness for such a beam. And it depends on the Young's modulus of the material, E, the area moment of inertia, I, and the length of the beam, L. From the formula we can see that the length has a very large influence because it appears in the formula as a third to the power of 3. The area moment of inertia depends on the steel beam's cross-section, where we can roughly say that the more material the cross-section has away from the central axis, the stiffer it will be for bending. Not just the steel structure has a stiffness, the pipe shoe also has a stiffness. And in the case where more complex structures are involved, we might have structures on top of structures in order to have combined stiffnesses. Not just the steel structure has a stiffness, the pipe shoe also has a stiffness. And depending on the design of the shoe, these can be either relevant or not relevant. When there are two things, each with a stiffness, and they are combined in series, then the combined stiffness can be calculated with the formula that's shown on the right here. The main takeaway from this formula is that if one of the two stiffnesses is much higher than the other, then the combined value will be close to that of the lower of the two. And when the stiffnesses are the same, then the combined value is roughly half of the individual stiffness. So in pipe stress analysis, as we discussed, rigid supports are commonplace. And then many stress analysis packages will assume a default stiffness for rigid support, which is, for in the case of CAESAR II, is 10 to the 12th of pounds per inch. And as we discussed before, for static analyses, this is often acceptable or will even lead to conservative designs. But for dynamic analysis, this will lead to an overestimation of the mechanical natural frequency of the system. The mechanical natural frequency of a spring mass system is given by this formula. So it goes with the square root of the stiffness, K, over the mass. And in case that the stiffness of a system is much higher, it's modeled much higher, we will also overestimate the mechanical natural frequency that's calculated. In this table, we show some typical values for axial support stiffnesses as defined in APA 688. If we compare the 10 to the power of 12 pounds per inch with the typical stiffness values, even at grade level with heavy duty supports and clamps, we reach roughly 250,000 pounds per inch is typical. So this is many orders of magnitude lower than what CAESAR will use as a default support value. If we then look at the actual modes of the system, those will be way off. So let's talk a little bit more about this resonance of systems. So let's take a look at what happens when we suddenly apply a load to a mass spring system. First off, if we apply a static load to a system, we can use a simple formula to calculate what would be the maximum displacement. And in the graph on the right here, I've indicated that with the orange line. If we apply this force dynamically, so on the left side we show the force versus time graph, where at time 0 no force is applied, and then it's very quickly ramped up to one value and kept constant after that. Then the response of this mass spring system will be that the system will first overshoot the static response value, then it will come back down and it will oscillate back and forth until it finally stabilizes on the on the same value as what we calculated from the static response. This type of graph we can use to calculate what's called a dynamic load factor. And the dynamic load factor is defined as the maximum response of the system in the dynamic case compared to the maximum response in the static case. So keep in mind that in both those cases the amplitude of the force is the same. It's just that the timing is different. In this graph, for this specific case, we find a DLF that's roughly 1.8. So the dynamic response of this shock load of 1 Newton is 1.8 times as much as the constant static load. And theoretically, for shock loads, a maximum value of 2 will be calculated. But what would now happen if we, instead of applying a shock load where we instantaneously raise the force to a constant value, but we can also vary the force with a specific frequency. Now it depends on the frequency of the force with respect to the system's mechanical natural frequency, how high this dynamic load factor can become. The maximum value is obtained when forcing frequency exactly matches the mechanical natural frequency. On the right side here, we have a formula that can be used to calculate what the dynamic load factor would be. And it's a function of the forcing frequency, omega f, the mechanical natural frequency, omega n, and beta, which is a damping ratio. On the left side, I've plotted this expression for a different number of damping ratios. And you can see that when the forcing frequency is very close to the mechanical natural frequency, so their ratio is close to 1, we can get a very high amplification of the movement. It is important to know that the API 688 specifies a damping ratio of 1% unless other values are available. And in the case of 1% damping, the DLF for a harmonically driven force on a mass spring system is 50. Meaning that the response of the system or the displacement can be 50 times as much as the static force when it's applied harmonically at the mechanical natural frequency. We have shown this formula before, the mechanical natural frequency of a mass spring system. If we look at an actual stop in a pipeline, and it will be modeled as, in air quotes, infinitely stiff, this would give an infinite resonance frequency. However, this is incorrect, and a realistic value of the stiffness could yield a mechanical natural frequency that's close to the excitation frequency. The API 618 code talks about separation margins to deal with this issue. And in order for a design approach 2 study to pass, the mechanical natural frequency of a support or of the piping system as a whole must be shown to be separated by at least 20% from the first and second harmonic of the excitation frequency. The excitation frequency will be fixed by the running speed of your compressor. As an example, if a compressor is running at 8 Hz, that means that the support should be so stiff that the mechanical natural frequency is at least higher than 19.2 Hz. So 20% over 2 times the base frequency. If axial supports are modeled as rigid, this might be achieved. But in reality, it's not straightforward to create a support structure that's so stiff that it will have a mechanical natural frequency this high, especially when the pipe is at an elevation. You can think back to the table that I showed before with the typical support stiffnesses. All this will serve as a warning to help you realize that when a dynamic study is performed, the supports need to be included in a more detail and what is required for a static analysis. But if this rigid supporting is not sufficient, how can we do it better? And this brings us to method number 2. So instead of modeling the restraints with an infinite stiffness or the very high default stiffness, the stiffness of the support will have to be calculated separately. And this can be performed, for example, by a structural department that does the calculation for your support structure, or by you yourself. And you can use various methods to calculate these stiffnesses, such as hand calculations, finite element calculations, and in some cases catalog data. Once those values are known, the stiffnesses can be input into your piping software. On the right here we have a screenshot of how this would look in BOSpulse to apply a stiffness to, in this case, the vertical support. Another method, which we'll call method number 3, includes the structural steel into the piping model. In this way, not only the stiffness of the structural steel is included, but also the mass of the frame that is joining in the movement. If there are multiple supports that connect to a single frame, for example the pipe bridge that is shown here, there can also be mechanical modes that you wouldn't find if you applied spring rates to the support nodes. So let's have a short overview of comparing of those modeling methods. Method number 1, in which we will assume that the supports are, in air quotes, infinitely stiff. This will overestimate reaction loads in static calculations, and as we discussed before, is not suitable to be used in dynamic analyses. The modeling effort is low and the computation speed is the fastest. So this method should be used for simple static stress analyses. Then method number 2, where we model the supports as springs, is a realistic way of doing static analysis, but does not have the same conservatism. And for this reason, method number 1 is preferred for the static analyses. Method number 2, however, is suitable to use for dynamic analyses. It lowers the calculated structural mechanical frequency to a realistic range based on the flexibility of the calculated support. In terms of modeling effort, it requires some additional steps to input the stiffnesses for each of the supports, and those need to be calculated, of course. The computation time is still fast. The additional stiffness adds some complexity, but the number of degrees of freedom for the system remain the same as in the method number 1. And finally, the integrated steel. So we include the structural steel in the piping model, and we use it as one coupled system. This is the highest level of precision, and it captures the complexity of the interaction of the frame and the piping together in the most detail. And for dynamic accuracy, we capture both the stiffness of the supporting structure as well as the mass of the supporting structure. And this might lead to a further reduction of the mechanical natural frequency. The modeling effort is somewhat higher because now, besides the piping, we also need to model the steel structure. And the calculation time is somewhat lower, although for the type of analyses that we're doing, this shouldn't be prohibitive. The best use cases for method number 3 are skid designs and offshore modules, especially when pipe sizes are similar size to the beam sizes. And also API 618 pulsation studies. The integrated steel is the best used method. To summarize a little bit, for standard piping, method 2 is a choice. If you have some kind of dynamic force, method 2 can be sufficiently accurate, especially if most of your supports are single support posts that are relatively close to the ground. However, for API 618 Design Approach 3 of reciprocating compressors, method 3 is effectively a requirement, as the stiffness of multiple elements, and not just the piping and the supports, but also the stiffness of the compressor body and the pulsation suppression devices needs to be accounted for in order to have an accurate prediction of the mechanical natural frequencies of the systems that are going to be used to calculate the vibration levels in order to pass the API assessment. Let's next have a look at a few examples of how we can use these modeling methods in our program. In this first example, we'll have a look at a small bore, it's 3-inch, venting gas line. It's been specified that a low frequency, so 2 to 4 Hz, vibrations were observed in the field with large axial displacements. And despite there being an axial stop, and this structure, the supporting structure of the axial stop, is shown on the right. The question is now, how could this be the case, as we have these large axial displacements? So let's first have a look at if we import this model into BOSpulse and see what the model will look like and how the mechanical natural frequencies are. So I have the model here in CAESAR. I'm going to first show our effortless import feature of BOSpulse for CAESAR models. So I'll close this CAESAR model. And then in the main interface of CAESAR, I will go to Interfaces, CAESAR II neutral file. So open a pop-up. This will allow me to convert the CAESAR II input file, so that's our model file, into what they call a CAESAR II neutral file. And this neutral file can be imported into BOSpulse. So press convert. And then once it's been finished, I say I don't want to do another one. And I can close out of CAESAR. I already have BOSpulse open with a new model, so nothing inside of it yet. I will import a file. I select the .CII file, or CAESAR II neutral file. Press OK. In this case, I would like not to merge the elements. And press OK, and now here we have it. So as you can see, the CAESAR model is fully compatible with BOSpulse. Here at this location, we have the axial stop, where the problem occurred. So we'll set up an analysis to look for the structural modes of this system. So as the analysis type, we'll select structural model, and as the input we can specify from which frequency to which frequency we want the software to find the mode. The introduction to the problems gave that frequencies between 2 and 4 Hertz were observed. So I think if we go up to 15 Hertz, we should be able to see more than we actually need to. Under piping code, there's a possibility to choose one of the different piping codes, and this will be used to calculate the stiffnesses and flexibility factors of bands and T-junctions based on this code. I'll select the B31J since this is the most accurate in terms of stiffnesses. Then I can go to run. We'll combine the main scenario with the analysis that we just started, and we can press the play button to run. In the background, this model will be sent to ANSYS solver, and the result will come back into BOSpulse. So it's already finished. So I'm able to visualize the results now. I will find that for the first natural mode, if I press play, you can see the movement. So indeed we see movement of this area, but it doesn't match with the observed large axial displacement. We look at the second waveform. We have a frequency of 5.9 Hertz. It's also moving differently than what was observed in the field. And then the next one is already at 9 Hertz, so it's a much higher frequency. So let's go back to the drawing for a little bit. So as we've discussed previously, now this axial stop is modeled as a rigid support, but is this actually a rigid support? And in order to assess that, we can have a look at the different parts of the steel structure. And the important thing for this example, what we want to look at is the axial stiffness. So that would be the for a force that's out of plane or in the axial direction of this piece of pipe. And we can do a calculation of what the bending moment, the stiffness would be of the different components. So we can identify the shoe, this I-beam, and this cylindrical support post. So first for the shoe, we can look at the cross section. We'll have, for the bending in the out of plane direction. So if we look at the cross section, so this would be a top of the cross section of this this plate under the support shoe. And we can calculate using standard formulas what would be the moment of area. Once we've calculated that, we can input that into this formula for the stiffness for this bending. We'll find a value of 82,000 newtons per millimeter. The same thing can be done for this beam. Now, something you might have already observed is that this beam is being loaded in the weakest direction. So we're going to have a force from left to right at the top here, and there's almost no material here that can withstand that bending. So schematically, we can look at this thing on the center here, and almost all the material is close to the central axis. So the the second moment of area, is going to be very small. And if we input that together with the height of the of this beam, we can find the value, total value for the stiffness of this beam against the bending in that direction to be only 60 newtons per millimeters. Now the same thing can be done for the cross section of the pipe here. We use a standard formula to calculate the moment of area again, using the inner and outer radius of this pipe, and we find a value of 14,000 newtons per millimeter. Finally, we can combine those in order to get the combined stiffness that we can apply on our restraint at the node here. And now in the if we combine those three, you can see that it's going to be dominated by the lowest one. So for the cross beam, it's 60 newtons per millimeter, and then the combined one is slightly below that value, so roughly 60 newtons per millimeter. So let's input that into our BOSpulse model. In the Scenarios tab, I will create a new scenario. So we'll call method 2. Where now we're going to make a variation of the main model inside this scenario, where under the support definitions, we'll look for the axial stop. In this case, it's in the X direction, and we can specify a stiffness value, and we'll input the 60 that we calculated before, or let's be precise, the 59.6. We'll press OK. Then under Run, we can also combine the new scenario with the same analysis type. If we run that, we can also have both results available to us, so we can use that to compare. So now, if we look at the lowest natural frequency, we find a value of around 4 Hertz, where we have this movement. So this already matches much better with the description that was observed by the people in the field. So there's another method that we can use. We can also model the steel frame. So let's do that. Let's do that next. We'll add a new element. We'll start by node number 5000 to be well away from all the other node numbers in the model. And we can use a ANSI scheduled 80 pipe, which was what the support was made out of. The diameter will be 4 inch, and then our database will automatically fill in the thickness corresponding to schedule 80. The length of this thing was 1400 millimeters, and it was in the Y direction. Right now it's located here at the bottom of the model because I haven't connected it to any piece, so it'll just be at the origin. Now on top of that, we want to model this I-beam. So BOSpulse has different structural beams included in the as options for structural members. So we press plus, we can add structural beams. We have I-beams, channel beams, T-profiles, L-profiles, rectangular beams, or a beam for which you can specify your own moment of areas. So it can be basically any profile. But remember that these profiles, what we're modeling, will always be the profile cross-section along the axis. And in this case, this beam is not along the axis, so this is perpendicular to the axis. So if we want to model the effect of this plate, we'll have to model just the plate. So what I will do here is I will select an R beam, which is just a rectangular beam, and I will input the height and width to match with the cross section. So it's 5 wide, and as a thickness, we'll put half of the half of the width, the total width of the cross section, so to make it a full, let's say a full square. The height of that thing was 250 millimeters. And we've already seen that this was actually the most flexible thing. So I will skip the modeling of the shoe for now, and we'll connect this directly to our model here. So this support node is node number 45. And then I'm going to make a new scenario where we will connect it to the system. Method number 3 will in this one we'll go to this support definition, and then we'll use connected node to connect it to the top of this I-beam profile. The same for the restraints in the other direction. So you can see it's not moved yet, but if we ask the software to update, we can move all the connected nodes to the same position. See that this one is specified as a rigid. It's not the case. It's just a piece of pipe. And then at the bottom of that piece of pipe, we'll put an anchor where it's restrained to the ground. Now we can run the analysis again. We'll add method number 3. And then, just to be sure, in method number in the main part, we'll remove this from the structural model, so that the other two scenarios don't have this part included. And method number scenario method 3, of course, will have to enable it again. Now we'll run the 3 cases again. You can see, have a little look at the differences. But here we find again a mode in which there's a large actual displacement at the at this actual stop, and in this case with including the supporting steel, and now we also include the masses here of this this piece of pipe that's moving, and we find a value of 3.5 hertz. So let's now move on to the next example. In this next example, we're going to have a look at this piece of piping that runs over a pipe bridge. In this case, the structural department has already provided us with the stiffness of the different supports on the pipe bridge. And I've already gone ahead and modeled that into BOSpulse. The next thing we'll do is we'll model the pipe bridge itself. And I'll show you how you can easily do that using the structural I-beam modeler. So let's go into BOSpulse. Here you can see the model. It's already as described. And under scenarios, I already have 2 different scenarios. One where the supports are modeled in rigids, and one where we've calculated the stiffnesses. We go to support. You can see that the stiffness for the Y direction, the guide, and the actual stop are already input. So next up, we'll show how you can relatively easily model a bridge structure as it is shown here. So we'll go to our modeling mode and start by creating a new element. I'm again going to start at 5,000, and in this case I'm going to go to 6,000. I'll start by modeling this leg here. So we'll go up 5 meters, and we'll change the element type to an I-beam. The profile was given here, so it's an HEA 120. It's a pretty standard beam. Used for the web height, these values. The web thickness is 5 millimeters and the flange thickness is 8. I know that in our case the beams are oriented in this direction, so I'll put a 90-degree rotation on it. I will also for now untick this box for structural modeler, so that we can again do the same thing as in the previous example, where for the other 2 scenarios these beams are not included, and then for the 3rd scenario I will include them. So I've modeled the first leg, and now I'm going to choose my node numbers in such a way that I can easily replicate the repeating structures. So first thing is, I see that there's a 0.5 meter distance between the corner and the place where we want to connect our with our pipe. So the next element I'm going to make is going to be 500 long, and it's going to be in the minus z direction. Now this one is again oriented in a different direction, so this will have to be 0. And as a node number, I'm gonna use 6100. And then I'll put the next one to 6200 with the remainder of the 2.5 meter. Next up, I will also add this this beam for 8 meters in the other direction, and for that I will start from node number 6000 and we'll go to 610. I will put it for 8 meters in the x direction. In order to more quickly model the rest of the structure, we can use the duplicate feature. I'll select all of these elements, right click, duplicate elements. Now I would like one copy and increment the nodes by 10, which will create from this one 5000, 5010. It's not connected anywhere. From this node, and anything connected to this node will be duplicated and will connect to this node. Now I can do the same thing for this this beam once more to make the final beam on the right side. So we'll duplicate it again with a node increment of 10. And now all we have left to do is to move or to duplicate the one side of the frame in order to make it on the other side as well. We'll duplicate it again. In this case, I've put a node step of 200 in between this side and this side. So we'll put it as an increment of 200. And I see that I've forgotten to select this this part the last time, so I'll do this one again for node increment of 10 again. All these supports are connected at the bottom with anchors. These not the supports, but the legs of this structure. So as a restraint, we'll input an anchor for all 6 of them. Apply the changes, so that's there. So there we have our structure. Now we'll make our scenario and connect it to this piece of piping. So we'll create scenario 3. And in this scenario, we'll start connecting these elements. So select the nodes, and then change the connected node from undefined to the 6100. Apply those changes and then do the same thing for this one, but this one's connected to 1 or 10 higher. Sorry, this is stiffness field. And finally, the last one will also be connected to the frame. You can change the coordinates again to tell the program to update the connected nodes. So now that we have the structural steel in place, we'll have to enable it for this third model, for this third scenario. So go to the elements in the third. We can double click the I-beams to select all the I-beams at once and turn them on in the structural model. And in order to make the analysis and the results a little bit more straightforward to interpret for this webinar, I've limited the piping in the other two scenarios to this, only the piping that's on the bridge. So I'll do the same for this last scenario that we just made. We'll select those and we'll disable them from the structural model. And then the same here. And disable them as well. We can go to the Run tab. We'll run our models. And then we can compare the computed mechanical modes between the different methods of analysis. At node number 1, we'll find a node at 0 frequency. So this in this case is an unrealistic mode, but it's because the rotation around the axis of this pipe isn't restrained anywhere. So there's it's free to move in that direction. We can visualize it. If I go to the X rotation, you'll see that the whole pipe is basically rolling in this mode. So this is not a real case, and we could have fixed that by applying a rotation restraint on one of these supports. So we'll ignore that one for now. But if we go to the let's say the first real mode, when we model with the rigid support, we see this kind of nice sine wave. It's at 11.8 Hertz, so relatively high. The next one is again at the same frequency, but it's in the vertical direction, and then we'll see higher modes where now the two sections are moving in phase with each other. The same thing, but in a different direction. And now here we see the higher waves, or we see let's say a double sine wave shape between each of these supports. We can compare that to the mechanical natural frequency that we find in the with the calculated stiffnesses. But now we find that there's also a very low frequency wave at 2.6 or 2.7 Hertz. And then also in the axial direction, there's a low frequency wave at 3 Hertz. If we go to the higher modes, we do eventually also find this mode that we found in the original one. It's at a slightly shifted frequency, but those are still found. But the most important thing to remember is that a mode like this would not have been found if we model rigid support. Now if I look at the modes from the structural steel, you'll see that now the mode shapes are a little bit more complex because they involve not just the piping itself but also the movement of the structural members. And if I go quickly through the different modes, they look like this. The second mode at 2.2 Hertz. The third one 2.5. And then at 11.3 we find again the where it started with the rigid support. Now you can imagine that if you have a lower frequency excitation in with the force in the axial direction, that it might be important to capture modes that are of this type of shape. So I hope I showed you how to model the different the different methods for applying the structural connections. In this example here, I did model the connection between the pipe and the supporting steel as a rigid connection. If you have, for example, clamps and they have a known or pre-calculated stiffness, then we could of course also connect the pipe through a restraint with the C node with the stiffness of the clamp to the structural steel, which would again have another effect on the calculated modes, but would be a more precise method of analyzing. So to bring it all back, what does this mean for a compressor study? So the API 618 demands an accurate calculation of the mechanical response. And in order to have an accurate calculation, we would need to include accurately the stiffnesses of the supporting structure, but not just the supporting structure, also of the compressor body itself. So on the right side here you see a screenshot of what that might look like for a compressor. So there's two throws, there's pulsation dampeners at the top and at the bottom. In the gray we have the internal gas passage, but we have not included that in the structural model, so that's why it's shown as transparent in this screenshot. So one important thing is that the crosshead, so this would represent the connection of at the crosshead, and the API 618 specifies that this should be modeled as a three-way stop with rotational and translational stiffnesses that have to be defined by the OEM. Then this beam in this case would represent the stiffness of the compressor body itself. So the cylinder, the piston would be moving back and forth in this direction, and this beam needs to have the right properties to be able to represent the stiffness of the cylinder casing. In some cases, there's a structural steel that's used to support the cylinders. That would have to be modeled. There's ground supports for the pulsation suppression devices. In some cases, these are mounted on some kind of spring supports rather than rigid support. There's also nozzle flexibilities that can be incorporated. These can be computed in different software package. For example, Nozzle Pro can be used to calculate the nozzle flexibilities in order to get as accurate a model as possible. So the main takeaway I hope you get from this webinar is that oftentimes for static stress analyses, supports are assumed to be rigid, and for static analyses this is a good conservative choice, but this is not a good conservative choice when we're looking at dynamic loading, as the rigid supports don't predict accurate mechanical natural frequencies. And as we've seen before, the overlap between the mechanical natural frequency and the driving, so the excitation frequency, for example, from pulsation forces, can give a much higher response than you would predict from static analysis. And in the case of pure resonance with the 1% damping, even up to a factor of 50. So in order to have an accurate forced mechanical response, it is necessary to model the structural steel, especially around the compressor manifold, in sufficient detail. Thank you for your attention, and we'll have some time for questions.